In 1984, in the southern Netherlands, a handful of engineers moved into temporary structures on a Philips factory site in a town called Veldhoven. The buildings were poorly insulated. Temperature swings caused their instruments to drift. They scrounged equipment from wherever they could find it. Some of them quietly suspected their managers didn't expect this venture to succeed. The expectations were so low that failure seemed almost predetermined. The venture was called ASML. Today, it is one of the most strategically important companies on Earth. Every advanced semiconductor in your phone, your laptop, the servers running artificial intelligence, the systems controlling modern vehicles, all of them depend on machines that only ASML can build. No other company, no other country, just this one Dutch firm that began in those makeshift labs 40 years ago. How did that happen? How does a company go from wooden shacks to becoming an irreplaceable node in the global technology supply chain? The answer involves physics, politics, personalities, and a willingness to pursue problems that everyone else had abandoned. But it starts with understanding the crisis that created ASML in the first place. By the early 1980s, Philips was a fading giant. It had been one of the largest electronics companies in the world during the 1960s and 70s, sprawling across everything from radios to lighting to semiconductors. The company had helped shape modern consumer electronics. It had invented the compact cassette. It had co-developed the CD with Sony. At its peak, Philips employed hundreds of thousands of people across dozens of countries. But internally, the organization had calcified. Decisions moved slowly through layers of committees. Engineers complained that good ideas died in bureaucratic review. Budgets shifted unpredictably, making long-term planning difficult. The semiconductor division, which had once been positioned as a European counterweight to American and Japanese manufacturing, was losing ground. Philips still employed talented people, but the institution had lost its momentum. The company had become a victim of its own size. Meanwhile, a smaller company called ASM International occupied the opposite end of the spectrum. Led by a man named Arthur Del Prado, ASMI had an entrepreneurial culture that bordered on chaotic. Del Prado was a risk-taker by nature. He pushed hard on technological bets, sometimes acquiring companies or pursuing product lines that seemed improbable. But his company was perpetually stretched thin financially. ASMI had developed important technologies in deposition and epitaxy, processes used to build up layers on semiconductor wafers, but it lacked the stability to scale consistently. If Philips represented the limitations of a mature bureaucracy, ASMI represented the volatility of a small firm trying to will itself into relevance through sheer effort. Neither company had a credible plan for lithography, the critical process of printing circuit patterns onto silicon wafers. And by the early 1980s, lithography had become the central bottleneck in semiconductor manufacturing. The patterns being printed were getting smaller. The optical systems required to print them were becoming more complex. Japanese companies, especially Nikon, had mastered precision optics in ways that European firms couldn't match. Canon was close behind. The Netherlands had competent optical researchers scattered across universities and research institutes, but nothing approaching system-level manufacturing at the leading edge. Lithography tools weren't just machines, they were the gatekeepers of Moore's Law. Without better lithography, chips couldn't keep shrinking. Without shrinking chips, the entire semiconductor industry would stall. Anyone who controlled lithography controlled the pace of technological progress. So Philips and ASMI did something neither would have done under normal circumstances. They formed a joint venture. Philips needed innovation but couldn't reorganize itself fast enough to produce it internally. ASMI needed resources and credibility it couldn't generate on its own. The arrangement was driven by necessity rather than shared vision. It was a small experiment, not a decisive industrial strategy. And that's how a group of engineers ended up in those wooden buildings in Veldhoven trying to build lithography tools that could compete with the best in the world. The location itself underscored how little priority the venture had. The temporary structures were cast-offs on a larger Philips campus. Inside, engineers improvised test environments with whatever equipment they could scavenge. Measurement tools were outdated. The labs had poor climate control. Temperature fluctuations caused optical components to expand and contract unpredictably, throwing off alignment. Some engineers assigned to the venture took it as a sign that management had already written off the effort. Others saw it as an opportunity precisely because expectations were so low. The first product, called the PAS 2000 stepper, came out in 1985. On paper, it was credible. It used many of the same fundamental principles as competing tools. In practice, when tested against Nikon's machines, it fell short. The overlay accuracy, how precisely one layer of the chip pattern aligned with the layers beneath it, wasn't consistent. Small thermal changes inside the housing caused distortions that the engineers struggled to predict. The machine would work well in some conditions and poorly in others. Customers looked at it, appreciated the effort, and then placed their orders elsewhere. For 6 consecutive years, ASML lost money. 6 years. That's a long time to keep failing while your competitors keep improving. Every year, Nikon and Canon refined their systems. Every year, the gap between what ASML could deliver and what the market demanded seemed to grow rather than shrink. Inside Philips headquarters, executives started questioning whether the joint venture made any sense. The lithography market was dominated by established Japanese players with deep expertise and proven track records. What was the point of throwing money into a Dutch effort that couldn't compete? Some wanted to fold ASML back into the main organization, absorbing whatever useful technology had been developed. Others preferred to shut it down entirely and write off the losses. The view from ASMI wasn't much more optimistic. Philips moved too slowly, Del Prado thought. The bureaucracy that hampered the parent company seemed to be infecting the joint venture. ASML's hybrid culture, half corporate, half startup, seemed directionless. It wasn't clear who had authority to make which decisions or how quickly those decisions could be implemented. But underneath all that uncertainty, a small group of engineers kept working on the fundamental problems: alignment, exposure stability, mechanical precision. They weren't waiting for organizational clarity. They were trying to understand why their machines didn't perform as well as Nikon's and what they could do about it. One of them was a young engineer named Martin van den Brink, who had joined ASML shortly after its founding. Van den Brink would eventually become the company's chief technology officer and one of the most important figures in the history of semiconductor manufacturing. But in the 1980s, he was already making his presence felt on the engineering floor. He was known for his unfiltered assessments. When a subsystem didn't meet requirements, he said so directly. When an assumption contradicted physical reality, he didn't soften the correction. His expectations were demanding. He wanted explanations grounded in data, not intuition or optimism. Younger engineers learned quickly that technical preparation was the only way to survive a review session with him. Show up without having done the analysis, and he would dismantle your presentation in front of everyone. These sessions weren't comfortable, they could be bruising, but they pushed ASML to operate with a rigor that Philips had struggled to maintain. That culture of directness, of confronting technical problems honestly rather than politically, would become one of ASML's defining characteristics. It wasn't enough to have a plausible theory, you had to have data. You had to understand why something was failing, not just observe that it was. By 1990, ASML's situation had become unsustainable. Philips decided to spin the company out as an independent entity. Officially, it was framed as a vote of confidence. The venture had potential and deserved autonomy to pursue it. Privately, many people inside ASML interpreted it as abandonment. Philips was washing its hands of a problem it didn't want to keep funding. Independence meant fewer constraints, but also fewer guarantees. If the next product failed, there would be no parent company to absorb the losses. ASML would simply cease to exist. The spin-out forced ASML to adopt more disciplined operations. It also clarified accountability in a way that hadn't existed before. When tools failed, responsibility no longer dissolved into layers of corporate oversight. It rested entirely with the engineers and managers in Veldhoven. There was no one else to blame. Then, in 1991, something finally worked. ASML produced an eye-line stepper, a machine using 365 nanometer illumination, that performed well. It wasn't revolutionary, it didn't leapfrog the competition, but it was stable, predictable, and met customer requirements. More importantly, it demonstrated that ASML could learn from failures and apply that learning systematically. The company had spent 6 years understanding why its machines underperformed. Now it was showing that it could translate that understanding into better products. Semiconductor manufacturers started to view ASML not as an experimental side project, but as a supplier capable of improvement. That shift in perception mattered enormously. Chip makers were making decade-long investments in manufacturing processes. They needed suppliers they could trust to be around and to keep getting better. ASML was beginning to earn that trust. Orders increased, revenue stabilized. For the first time in its existence, ASML had a foundation to build on. In 1995, the company went public. The capital raised allowed ASML to expand its engineering teams, invest in better testing facilities, and strengthen relationships with suppliers. The IPO also sent a signal to customers. ASML intended to be around for the long term. This wasn't a company that would disappear after a few bad quarters. During these years, ASML deepened its relationship with Carl Zeiss, the German optics company. Zeiss had been making precision optical instruments since the 19th century. It was a world leader in microscopy, medical devices, and industrial measurement systems. The company had capabilities ASML couldn't replicate internally: deep expertise in optical design, precision manufacturing of lenses and mirrors, and testing methodologies that ensured performance at the limits of physics. Early collaborations revealed cultural differences. Zeiss engineers adhered to strict processes. They controlled lab environments meticulously. They carefully modeled tolerances before fabricating anything, then tested exhaustively to verify that reality matched predictions. ASML engineers, coming from a more improvisational background, often pushed for rapid prototyping and experimental iteration. Just build something and test it, they argued. You learn more from real experiments than from simulations. Initial meetings sometimes stalled over disagreements about measurement methodology or acceptable deviation. Zeiss engineers thought ASML moved too fast and didn't document enough. ASML engineers thought Zeiss moved too slowly and got lost in analysis. But the partnership persisted because both sides recognized they needed each other. ASML could move faster and integrate systems. Zeiss could achieve optical performance that ASML's internal teams couldn't reach. This mutual dependence laid the foundation for the multi-decade collaboration that would later make extreme ultraviolet lithography possible. As ASML grew through the late 1990s, its engineers confronted the limitations of their existing machine architectures. They needed more throughput, more wafers processed per hour. They needed faster wafer handling. They needed better stability at smaller geometries, where any vibration or thermal fluctuation could ruin a pattern. These pressures led to the development of a platform called TwinScan around the year 2000. TwinScan introduced dual wafer stages. Traditional steppers had one stage: load a wafer, align it, expose it, unload it, repeat. TwinScan had two stages working in parallel. While one wafer was being exposed, the next one was being aligned on the second stage. When the exposure finished, the stages swapped positions. The result was significantly higher throughput without sacrificing accuracy. The concept wasn't entirely new. Others had proposed dual-stage systems, but ASML industrialized it faster and more effectively than competitors expected. Nikon hadn't anticipated how quickly ASML could bring the technology to market. Canon was already losing ground. For the first time, ASML held a genuine technical advantage over both Japanese competitors. The company that had started in wooden shacks was now leading the industry in at least one important dimension. This momentum emboldened ASML to commit to technologies that seemed risky. Immersion lithography was one of them. Traditional lithography used air between the lens and the wafer. Light passed through the final lens element, traveled through a small air gap, and then struck the photoresist on the wafer. This worked fine at larger feature sizes, but as patterns shrank, the physics became limiting. The numerical aperture of the optical system, a measure of how much light it could gather and focus, was constrained by the refractive index of air. Engineers proposed filling that gap with ultrapure water instead of air. Water has a higher refractive index than air, which increases the effective numerical aperture of the optical system. In practical terms, this meant finer resolution, smaller features could be printed, Many people in the industry doubted immersion would work reliably at manufacturing scale. Water and semiconductors didn't seem like a natural combination. Fluid dynamics introduced unpredictable variables. Any bubbles or particulates in the water could ruin the exposure pattern. The water had to flow continuously to prevent contamination buildup, but that flow created its own challenges: vibration, temperature gradients, pressure variations. ASML built early prototypes that confirmed many of these concerns. Flow rates were unstable, contamination accumulated faster than expected, mechanical vibration from pumping systems coupled into the optical path and degraded image quality. The technology worked in principle, but not in practice. But instead of abandoning the concept, ASML invested heavily in refining it. Engineers redesigned flow geometries to create laminar flow patterns that minimize turbulence. They introduced better filtration systems to remove particles down to nanometer scales. They developed new contamination control systems that could detect and respond to problems in real time. They characterized every variable they could measure and built models to predict behavior under different conditions. When immersion tools finally reached the market, they performed reliably enough for high-volume manufacturing. Customers were initially skeptical, but the resolution improvements were undeniable. ASML's market share grew sharply. By the time competitors caught up with their own immersion systems, ASML had established itself as the leader. Throughout these developments, Van den Brink continued to shape the engineering culture. He pushed teams to think in terms of system-level interactions rather than isolated subsystems. A lithography tool wasn't just a collection of components, it was a system where every part affected every other part. His approach required wafer stage engineers to understand optics, optics engineers to understand thermal mechanics, and software teams to understand the limitations imposed by physics. This cross-disciplinary pressure prevented narrow thinking. It also prepared ASML for the far greater complexity that lay ahead. By the early 2000s, ASML was no longer an underdog fighting for survival. It had surpassed Nikon in key areas, earned deep trust from major chip manufacturers, and established itself as a credible leader in advanced lithography. But the company's future would not be shaped by immersion, lithography, or twin scan. It would be shaped by the long-delayed promise of extreme ultraviolet light, a technology that had been discussed for decades, researched in government laboratories, and pursued half-heartedly by multiple institutions, but never made commercially viable. EUV would require coordinating physics, optics, plasma generation, contamination control, manufacturing, and software on a scale no company had ever attempted. ASML entered that era with advantages it hadn't possessed in the past: a disciplined engineering culture, a mature partnership with Zeiss, and a track record of solving problems that competitors had walked away from. Those strengths would be necessary because EUV would test every assumption ASML had about how lithography systems were built. The company was about to enter the most difficult engineering chapter in its history, one that would demand not only money and time, but complete organizational endurance. ASML entered the 2000s with a degree of stability it had never known before. The company had reliable revenue from its steppers, a growing customer base, and a maturing engineering organization. But internally, there was recognition that this stability could not last. The semiconductor industry was already pushing up against the physical limits of 193 nanometer lithography. Even immersion, which ASML had embraced more aggressively than its competitors, wouldn't carry the industry indefinitely. There were tricks to extend the technology: double patterning, where the same layer was exposed twice with different masks, and later quadruple patterning. But these added cost and complexity. Every additional patterning step meant more time, more defect opportunities, more expense. The industry was running out of runway. If transistor scaling was going to continue, a shorter wavelength would eventually be necessary. That meant extreme ultraviolet, light with a wavelength of just 13.5 nanometers. To put that in perspective, the wavelength ASML had been using for immersion was 193 nanometers, more than 14 times longer. EUV wasn't just an incremental improvement, it was a different category of physics. The concept had been studied in national laboratories since the 1980s. Researchers at Sandia, Lawrence Livermore, and Lawrence Berkeley in the United States had demonstrated basic EUV principles. They had shown that it was possible to generate EUV light and use it to create patterns on photoresist, but no organization had come close to making it practical for manufacturing. Laboratory demonstrations showed promise, but throughput was low, stability was poor, and contamination destroyed the optics quickly. Moving from demonstration to production would require coordination between plasma physics, precision optics, mechanical engineering, vacuum systems, and software in ways that had never been attempted. Each individual challenge was daunting. Combining them into a working system seemed nearly impossible. It was clear that EUV couldn't succeed without external partners. The most critical was Carl Zeiss, which would need to develop optical systems unlike anything it had built before. EUV light can't pass through glass, it's absorbed almost immediately. That ruled out conventional lenses. Instead, the optical system would need to use mirrors, and those mirrors would need to be perfect to a degree that pushed the boundaries of what humans could manufacture. But there was another partner, less visible publicly and more decisive in outcome. That partner was TSMC, under the leadership of Morris Chang. TSMC had already been playing an outsized role in ASML's trajectory for more than a decade. In the early 1990s, when ASML's tools were still inconsistent, TSMC evaluated them with more openness than other chip makers. Morris Chang had founded TSMC in 1987 with a radical idea. Instead of designing and manufacturing its own chips, TSMC would manufacture chips designed by other companies. This foundry model upended the industry's vertical integration. It allowed fabless design companies to exist, firms that could design cutting-edge chips without building billion-dollar factories. To make the foundry model work, TSMC needed the best manufacturing technology, regardless of where it came from. Chang encouraged his teams to test any equipment that might offer a process advantage, regardless of vendor reputation. American and Japanese integrated device manufacturers were more rigid in their supplier relationships. Intel was deeply committed to Nikon. Japanese manufacturers trusted domestic suppliers. TSMC, still relatively young and unconstrained by legacy relationships, was motivated to experiment. ASML benefited from this willingness. TSMC's engineers generated real manufacturing data on ASML tools before the company had fully earned that trust. They documented failure modes with unusual transparency, providing ASML with empirical evidence to improve alignment systems, thermal control, and overlay performance. Most customers treated their manufacturing data as proprietary secrets. TSMC shared enough of it, carefully, selectively, to help ASML improve. For ASML, this feedback was more valuable than many of its own internal tests. It allowed the company to iterate against real manufacturing conditions instead of guessing from laboratory simulations. By the late 1990s, when immersion lithography emerged as a possible successor to dry 193 nanometer tools, TSMC once again played the role of early evaluator. Morris Chang had built a corporate culture that prioritized process stability over corporate symbolism. If a technology worked, TSMC adopted it quickly. If it didn't, TSMC documented why. This approach gave ASML a customer whose incentives aligned with rapid technical progress. The early immersion prototypes were unreliable, with unstable water flow and contamination issues, but TSMC committed engineering resources to characterize the problem systematically. That collaboration gave ASML the data it needed to redesign flow geometries, improve filtration, and build better contamination control. Immersion ramped faster in Taiwan than anywhere else, and ASML's share grew accordingly. EUV posed challenges far beyond immersion. The fundamental issue was the light source. Generating EUV required firing high-energy laser pulses at droplets of molten tin to produce plasma that emitted 13.5 nanometer radiation. The process worked like this. A laser would create tiny tin droplets, perhaps 50,000 per second. Another, more powerful laser would vaporize each droplet, creating a plasma hot enough to emit EUV light. That light would then be collected by mirrors and directed through the optical system to the wafer. This process was inherently unstable. Droplet timing varied. Even small variations in droplet size or position affected the plasma characteristics. Debris from the vaporized tin interfered with optics, coating mirrors with material that degraded their reflectivity. Light output fluctuated unpredictably. The source needed to produce sufficient power, measured in hundreds of watts of EUV light, to achieve economically viable throughput, but early sources produced only a fraction of that. To gain more control, ASML acquired Cymer, an American company based in San Diego with expertise in high-power laser systems. Cymer had been making Excimer lasers for DUV lithography and had begun working on EUV source technology. The acquisition brought critical expertise in-house, but even with Cymer's capabilities, stabilizing the plasma source required years of iterative experimentation. The physics were unforgiving. You couldn't just engineer your way around the fundamental instabilities. You had to understand them deeply enough to work within their constraints. The optical system presented a different set of barriers. Because EUV light can't pass through lenses, mirrors were the only option. These mirrors, designed and manufactured by Zeiss, consisted of dozens of alternating thin layers of molybdenum and silicon deposited with nanometer-scale precision. Each layer had to be exactly the right thickness. The surface had to be smoothed to within fractions of an atomic diameter. Small deviations in those layers caused wavefront distortions that degraded image quality. Contamination from the tin plasma, from outgassing materials inside the vacuum chamber, from any number of sources, degraded reflectivity over time. Thermal expansion from absorbed EUV light introduced alignment errors. Every mirror required active cooling and exceptional mechanical stability. The mirrors weren't just difficult to make, they were difficult to keep working. Engineers from Zeiss and ASML spent years refining designs and testing prototypes. The collaboration was intense, with frequent travel between Veldhoven and Oberkochen. The two companies debated everything from coating thickness to mechanical mounting strategies, gradually converging on a system that could survive the brutal conditions inside an EUV scanner. This wasn't a typical vendor relationship. It was a genuine partnership where both sides contributed expertise and both sides shared risks. While ASML and Zeiss tackled optics and plasma physics, TSMC played a critical external role. Chip manufacturers weren't simply future customers for these machines, they were co-developers. EUV was too complex for a supplier to build in isolation. The equipment maker needed feedback from the fab floor about how the tools actually performed under manufacturing conditions. TSMC ran simulations, evaluated prototype exposure tools, and provided detailed process feedback. Morris Chang understood that being early to EUV would pay dividends not because the tools themselves were unique, but because early operational experience would produce institutional knowledge that competitors couldn't easily replicate. TSMC would learn how to run EUV tools, how to optimize yields, how to integrate EUV into its process flows. That knowledge would take years to accumulate. Getting started early was itself a competitive advantage. This view shaped TSMC's internal incentives. Chang encouraged deep collaboration with ASML engineers, allowing them to run experiments inside TSMC fabs and collect high-volume manufacturing data. TSMC treated ASML not as a vendor to be managed at arm's length, but as a partner whose success was aligned with its own. This collaboration became more formal in 2012 when ASML launched a co-investment program. The company needed billions of dollars to continue EUV development, and it sought contributions from its largest customers. Intel made the first and largest public move, acquiring a minority stake in ASML. Samsung followed, but TSMC's participation mattered more from an operational standpoint. Morris Chang viewed the investment not simply as financial support, but as strategic alignment. He wanted EUV to remain a shared industry platform, not a technology directed by any single company's agenda. Intel was an integrated device manufacturer. It designed and built its own chips. Its interests weren't necessarily identical to TSMC's. By investing directly, TSMC ensured that ASML's development priorities would reflect foundry needs as much as the preferences of integrated device manufacturers. The foundry model required high throughput, predictable uptime, and process uniformity across diverse customer designs. A foundry ran dozens of different chip designs through the same machines, each with different requirements. Tools needed to be stable and consistent, not optimized for one particular product. ASML's engineering focus shifted accordingly. This influence helped accelerate work on software stability, contamination control, and stage reliability, areas essential for high-volume production. As EUV prototypes improved, TSMC continued supplying practical insights that shaped the tool architecture. Early systems suffered from excessive downtime and inconsistent output. TSMC's engineers documented these failures in detail, providing logs, thermal data, and process correlations. The volumes of data produced at TSMC far exceeded what ASML could generate internally. This allowed ASML to diagnose failure modes sooner, refine control algorithms, and prioritize engineering resources more effectively. When the first commercial EUV systems shipped, TSMC absorbed more of them than any other manufacturer. The learning effects were immediate. TSMC ramped EUV yield more effectively than Intel or Samsung, not because it had more machines, but because its manufacturing organization was structured to integrate new tools with minimal disruption. TSMC had been preparing for EUV for years. It had trained operators, refined procedures, and built the organizational capability to absorb new technology quickly. The feedback loop between ASML and TSMC accelerated improvement on both sides. ASML began testing new software patches and hardware upgrades first in Hsinchu because the environment was stable and the engineering teams were responsive. This made TSMC's fabs into de facto development labs for the most advanced lithography on Earth. As ASML moved beyond standard EUV toward high numerical aperture EUV, the next generation of the technology, TSMC's influence became even more pronounced. High-NA tools were physically larger, more complex, and required entirely new building specifications. TSMC committed early to modifying its facilities to accommodate them. Its engineers participated in design reviews focused on reticle heating, stage acceleration, and process integration for next-generation nodes. While Zeiss developed the optics and Cymer worked to extend source power, TSMC evaluated how high NA exposure would interact with resist behavior, etch steps, and overlay budgets across multi-patterned layers. This integration was essential. High NA's value depended not only on optical resolution, but on how well fabs could incorporate the tool into a complete manufacturing sequence. Throughout this period, ASML had to balance aggressive development with operational stability. The company now maintained hundreds of EUV systems across multiple continents. Field teams supported installations, downtime events, and ongoing upgrades. The complexity of service increased as more layers in customer process flows moved to EUV. TSMC's fabs became central training environments for ASML's field engineers. The company refined its support protocols using lessons learned from Hsinchu, Taichung, and Tainan, then exported those protocols to customers in other regions. What worked in Taiwan became the template for the rest of the world. By the time High-NA entered late-stage development, the relationships among ASML, Zeiss, Cymer, and TSMC had become inseparable from the technology itself. EUV's performance depended on Zeiss's mirror precision, Cymer's light source stability, ASML's system integration, and TSMC's manufacturing discipline. No single organization could have delivered EUV on its own, but Morris Chang's early willingness to evaluate ASML tools, his support for collaborative engineering, and his insistence on operational rigor gave ASML something that no amount of internal expertise could have provided: continuous, large-scale, real-world feedback from the world's most advanced foundry. This partnership shaped the arc of EUV adoption. Intel initiated the co-investment program, but TSMC became the operational anchor that validated EUV for high-volume production. As the technology matured, ASML increasingly relied on TSMC to test upgrades, characterize new failure modes, and validate performance metrics. The relationship helped EUV transition from a research concept to a production standard. The collaborations that enabled EUV also reshaped ASML itself. The company expanded its engineering staff, reorganized its development processes, and grew into one of Europe's most important industrial institutions. But the foundation of this growth was built on cooperation between ASML, Zeiss, and TSMC, a triangular partnership constructed not on ideology or national interest, but on shared technical necessity and consistent execution. By the time EUV entered high-volume manufacturing, ASML had become something the semiconductor industry had never seen before, a single point of dependency for the most advanced stage of chip production. No other company had anything close to an alternative. Nikon and Canon had abandoned EUV years earlier. Both had made early efforts, but the technical challenges and investment requirements proved too daunting. They retreated to segments of the market where they could compete, mature nodes, specialty applications, and ceded the leading edge to ASML. No government research program was capable of turning laboratory systems into production tools. The United States had kickstarted the foundational physics in national laboratories, providing crucial early research. But America didn't maintain a domestic industrial base capable of building complete lithography systems. The expertise had migrated to Europe and Asia over decades. Following the migration of semiconductor manufacturing itself, ASML found itself holding the only viable path forward for advanced nodes, and the consequences of that position became clear almost immediately. Demand outpaced supply. ASML could produce only a limited number of EUV systems each year because the machines required thousands of highly specialized components sourced from hundreds of suppliers. A single projection optics system from Zeiss required nearly a year to manufacture. Each subsystem had its own supply chain, and delays anywhere caused cascading effects throughout the production schedule. ASML's planners learned to track each critical component individually, adjusting schedules constantly to prevent bottlenecks. They developed sophisticated models to predict delivery times, factoring in everything from raw material availability to supplier capacity utilization to shipping logistics. Even with extensive planning, the company couldn't increase output as quickly as customers wanted. The constraint wasn't money or willpower, it was physics and manufacturing complexity. TSMC, Samsung, and Intel competed for priority. Each wanted as many machines as they could get as quickly as possible. TSMC had the most consistent orders and the most predictable installation environments, which made it an attractive customer from ASML's perspective. When ASML shipped a machine to TSMC, it could be confident the tool would be installed properly and brought to productive use quickly. Samsung placed large orders, but sometimes revised timelines based on internal strategy shifts. Intel struggled with its own process delays, which affected its tool requirements from quarter to quarter. A machine ordered for one process node might not be needed until a later one. ASML had to manage these competing demands while remaining neutral. Any perception of favoritism could destabilize the industry. If one customer believed ASML was giving preferential treatment to a competitor, it might seek alternatives, even if no real alternatives existed. The company relied on long-term agreements and transparent schedules to maintain trust. Customers could see where they stood in the queue and understand why. The supply chain supporting EUV evolved into a complex international network. More than 300 suppliers were based in the Netherlands. Another 100 operated across Germany and the rest of Europe. Several critical suppliers were located in the United States, particularly those focused on lasers, vacuum systems, and high-performance materials. Each supplier had to meet stringent quality standards. ASML implemented what it called a zero defects policy, requiring components to pass extensive testing before integration. The company couldn't afford to discover problems after assembly. A defective component buried deep inside an EUV tool could require weeks of disassembly and repair. Prevention was far more cost-effective than correction. If a part failed inspection, the entire module could be delayed. Suppliers sometimes struggled to meet these expectations. ASML deployed its own engineers to assist or audit production at key sites. In some cases, ASML directly funded supplier expansions or acquired companies outright to secure critical expertise. The goal was always the same: ensure that no single failure could jeopardize the delivery of an EUV tool. The company's role as a system integrator became more pronounced. ASML didn't fabricate most of the components in its machines, but it defined specifications, orchestrated timelines, and integrated all the parts into functional systems. This position gave it significant influence over suppliers, but also made it dependent on their stability. If a supplier experienced financial issues, manufacturing setbacks, or quality inconsistencies, ASML had to intervene. Service requirements added another layer of complexity. EUV systems required continuous maintenance, software updates, spare parts, and environmental monitoring. Uptime targets were strict because every hour of downtime in a leading-edge fab translated into significant financial losses, potentially millions of dollars. ASML established service hubs near major customer sites, employing thousands of field engineers who worked in shifts to provide round-the-clock support. These teams often spent months inside customer fabs, assisting with calibrations, repairs, and process integration. This intensive service model resembled the aerospace industry more than traditional semiconductor equipment suppliers. Instead of shipping a machine and offering periodic support, ASML delivered a system that required continuous involvement. Software teams released updates to improve throughput or correct performance deviations. Mechanical engineers monitored stage behavior and vibration data. Optics specialists analyzed mirror degradation patterns. Plasma experts tracked light source stability. Feedback flowed constantly from customer fabs back to Veldhoven and Oberkochen. Improvements were deployed across the installed base as soon as they were validated. As ASML's strategic importance grew, so did political attention. Governments recognized that advanced semiconductor manufacturing depended on EUV tools. The chips powering artificial intelligence, advanced weapon systems, communications networks, and data centers all required the most advanced manufacturing processes, and those processes required ASML machines. Control over ASML meant influence over the pace of technological progress worldwide. The United States, concerned about the rise of China's semiconductor industry, pressured the Dutch government to restrict ASML from exporting EUV systems to Chinese manufacturers. The Netherlands, balancing its relationships with both the US and China, implemented licensing requirements that effectively barred the sale of EUV to China. This created tension. China was a significant market for older lithography tools, and ASML valued access to all global semiconductor regions. The company attempted to remain politically neutral, emphasizing that export decisions rested with government authorities, not with ASML itself. But neutrality was increasingly difficult to maintain as geopolitical pressures intensified. TSMC's involvement further complicated the geopolitical landscape. As the world's leading foundry, TSMC held the majority of EUV systems in operation. This concentrated a critical portion of global semiconductor capacity in Taiwan, a region already central to geopolitical tensions between the United States and China. ASML had to coordinate closely with TSMC on delivery schedules, facility preparation, and long-term roadmap alignment. The interdependence between ASML and TSMC became a structural feature of the industry and a source of strategic vulnerability that governments couldn't ignore. The expansion of EUV adoption also exposed logistics challenges. Transporting an EUV system required dozens of containers, specialized lifting equipment, and significant coordination between ASML, airlines, shipping companies, and local infrastructure providers. A single machine might weigh over 150 tons and stretch across multiple cargo planes. Installation inside fabs could take weeks or months. Clean rooms had to meet strict vibration and air quality requirements. Floors sometimes needed reinforcement to support the tool's weight. ASML worked with construction teams, facility engineers, and contamination control specialists to prepare sites. Each installation became a large-scale project involving hundreds of personnel. The company's internal structure changed in response to these demands. ASML expanded its workforce rapidly, hiring physicists, software engineers, mechanical designers, systems architects, logistics specialists, and field service personnel. The company that had started with a few dozen people in wooden shacks now employed tens of thousands across multiple continents. As headcount grew, informal communication channels that had worked in earlier decades became insufficient. The organization developed more formal processes for managing technical dependencies, evaluating design changes, and coordinating between teams. This transition wasn't always smooth. Some engineers preferred the old, less hierarchical style. Others recognized that the scale of EUV development required new systems to prevent misalignment and delays. Even with EUV deployed in production, the technology continued to evolve. Throughput improvements were essential. Customers needed higher wafer per hour rates to justify the cost of the tools. ASML developed new laser modules, thermal stability systems, and software optimizations to improve performance. These upgrades were deployed to both new and existing installations. A machine delivered in 2020 could be substantially different from the same model delivered in 2023 thanks to continuous improvement. High-NA EUV development ramped alongside these improvements. The new system's size and complexity forced ASML and its customers to think in terms of multi-year infrastructure plans. TSMC began preparing facilities well in advance, modifying buildings and updating environmental controls. Samsung and Intel evaluated similar investments but moved at different paces. ASML had to coordinate these developments carefully to ensure supply chain stability. High-NA systems would require more advanced components from Zeiss, more powerful light sources from Cymer, and new mechanical subsystems built by specialized suppliers across Europe and the United States. Each advancement required parallel investments throughout the supply chain. Despite the challenges, ASML maintained momentum because the foundational relationships supporting EUV remained strong. TSMC continued to provide manufacturing data that shaped system improvements. Zeiss refined mirror technology and increased production capacity for larger optics. Cymer worked on increasing light source output and stability. Suppliers across the network scaled operations to meet growing demand. As ASML's role solidified, the company became a central figure in discussions about global technology security. Policymakers realized that the world's most advanced semiconductors required tools from a single Dutch company. Industry analysts tracked ASML's production capacity as a leading indicator of global supply constraints. Investors viewed the company as a long-term strategic asset whose importance would persist regardless of cyclical fluctuations in semiconductor demand. What made this position unique wasn't simply that ASML had a monopoly. It was that EUV represented a technical frontier where no one else had the capability, experience, or accumulated data to compete. This wasn't the result of protectionism or luck. It was the product of decades of coordinated engineering work, long-term customer partnerships, and a corporate culture that prioritized accurate problem-solving over short-term advantage. As EUV matured and ASML expanded, the company faced a transition that rarely goes smoothly in technology. The shift from a founding generation of technical leaders to a broader, more distributed engineering organization. For decades, ASML's culture had been shaped by individuals with strong personal influence. People like Martin van den Brink and the core group of engineers who had grown alongside the company from its earliest days. They operated in an environment where improvisation, intense debate, and direct confrontation were normal and often necessary. That approach worked when teams were small, dependencies were limited, and most of the work occurred under one roof. But as EUV scaled and as ASML employed tens of thousands of people spread across continents, the company needed new structures to maintain technical discipline without relying on individual personalities. The earliest signs of this shift appeared quietly. Engineers hired in the 2010s entered an organization that looked very different from the one described in early accounts. The company now had formal processes for version control, design verification, and subsystem ownership. Documentation standards were higher, safety protocols were stricter, daily operations were less improvisational. This didn't mean the company had become bureaucratic. It reflected the reality that EUV tools required coordination on a scale that couldn't depend on informal knowledge. When thousands of engineers worked on a single machine, they needed shared frameworks for communication and decision-making. Institutional processes replaced personal relationships as the glue holding the organization together. Many early technical leaders remained deeply involved. Van den Brink continued to oversee engineering decisions with his characteristic directness. His technical instincts, informed by decades of experience, still carried significant weight. but he was surrounded by a growing number of system architects, domain specialists, and team leads who had developed their own areas of influence. The company no longer had a single center of gravity. Instead, it had multiple technical nuclei: optics, stages, software, plasma source, contamination control, mechatronics, each led by experts whose careers had been shaped by EUV's incremental evolution. In optics, the next generation of leaders worked closely with Zeiss counterparts who had developed mirror manufacturing techniques that hadn't existed when the collaboration began. These engineers understood not only the theoretical principles of multilayer mirrors, but also the manufacturing realities that constrained performance. They were responsible for integrating new materials, refining deposition processes, and improving surface flatness beyond previous limits. In mechatronics, a separate cohort of engineers developed expertise in the wafer and reticle stages. These systems had evolved into some of the most complex moving mechanisms in industry, combining high acceleration, low vibration, and extreme positional accuracy. The engineers responsible for these systems often had backgrounds in advanced robotics, precision machining, and control theory. They analyzed stage performance using detailed telemetry data collected from customer fabs, identifying small deviations that indicated emerging mechanical issues. Software had become its own world inside ASML. EUV systems depended on millions of lines of code to manage exposure settings, vibration compensation, alignment routines, and diagnostics. The software teams grew rapidly and adopted practices common in large-scale, safety-critical development: code reviews, automated testing, continuous integration pipelines, modular architectures. These practices were necessary not only for reliability, but also for the pace of updates required to support customers like TSMC, which integrated new software versions into production environments frequently. Contamination control also developed into a specialized discipline. Engineers in this area had to understand how tin, plasma, byproducts, hydrocarbons, and microscopic particles interacted with EUV optics and internal surfaces. They studied vacuum chemistry, surface adhesion, and gas dynamics to predict contamination behavior under different conditions. This work often intersected with mirror development, as even small improvements in contamination resistance could extend optics' lifetime significantly. As the engineering core diversified, ASML faced the challenge of maintaining a coherent culture. The original generation had built the company during a period when success depended on individual initiative and risk tolerance. Newer engineers joined an organization where success required careful coordination and adherence to established processes. The company addressed this by integrating early career engineers into cross-disciplinary teams where they could see how decisions in one area affected the entire system. Instead of learning from one or two dominant figures, they learned from a network of specialists who collectively embodied the company's accumulated knowledge. Leadership recognized that ASML needed to preserve the directness and analytical rigor of its early years, while reducing dependence on individual personalities. To achieve this, the company invested heavily in internal technical training. It developed programs for system engineering, optics fundamentals, plasma physics, and contamination control. These programs aim to propagate institutional knowledge systematically. Engineers who joined ASML after the EUV breakthrough were expected to understand not only their specific domain, but also how their work intersected with others. The shift toward institutionalizing knowledge didn't diminish the influence of key figures. Van den Brink continued to challenge engineers in design reviews, often identifying subtle flaws or pushing teams to rethink assumptions. But by this stage, he worked within a larger structure where system architects and team leads carried significant responsibility for technical decisions. The company no longer hinged on one person's judgment. It had built a hierarchy of expertise that distributed decision-making more effectively. This transition was essential because the company's growth had changed the nature of its responsibilities. In the 1990s and early 2000s, ASML's impact was limited by its market share. Its successes and failures influenced customers, but they didn't shape global capacity. By the 2020s, the consequences of any miscalculation were much larger. If ASML delayed a product by 6 months, it could disrupt the roadmaps of the world's largest chip manufacturers. If a supplier failed to meet quality standards, entire fabs could be affected. If a design decision introduced instability into production tools, it could impact industries far removed from semiconductors, automotive, aerospace, medical devices, consumer electronics. To manage this scale, the company invested in more formalized risk assessment. Technical decisions were documented carefully. Design changes required approval from multiple domain experts. Engineers built predictive models to evaluate how modifications would interact with the rest of the system. This rigor didn't slow progress. It reduced the likelihood of costly errors and improved the reliability of new releases. The company also restructured its approach to account for the growing complexity of global operations. Internal teams responsible for development, manufacturing, and service were integrated more closely. Feedback from customer fabs, especially TSMC, was incorporated into development cycles faster. ASML created structures to ensure that learnings from field failures, performance deviations, and installation issues flowed back into engineering in a consistent and usable form. This closed-loop system was essential for maintaining tool performance at scale. The transition to a larger, more structured organization also affected interpersonal dynamics. Younger engineers didn't experience the same environment of constant crisis that defined ASML's early years. They entered a company that was established, respected, and financially strong, but this stability brought new expectations. They were expected to maintain an uninterrupted trajectory of technological progress in an environment where the margin for error was shrinking. The company's leadership emphasized that EUV's success was not the endpoint, but the baseline. High NA would require even greater coordination and deeper expertise. Improvements to existing EUV systems would demand sustained attention to detail. The industry's expectations had grown faster than the company's workforce, and the responsibility to meet those expectations fell increasingly on the next generation. At the same time, ASML's culture remained distinct from many large technology corporations. Engineers were encouraged to challenge assumptions. Meetings involved direct questioning of analyses, not deference to seniority. When disagreements arose, they were addressed through data and technical reasoning. This culture had developed organically under Van den Brink and his peers, but by the 2020s it had become institutional. New engineers learned it not from a single leader, but from teams that embodied the values of rigor, clarity, and accountability. The growing engineering core also made ASML more resilient. Knowledge was no longer concentrated among a small group. System behavior, failure modes, and improvement paths were documented, shared, and maintained across teams. When senior engineers retired or moved into advisory roles, their expertise remained embedded in the organization. This was essential for sustaining progress on multi-decade projects like high-NA EUV, which required continuity even as personnel changed. As ASML continued evolving, the company maintained a focus on the same core principles that had carried it through earlier chapters: solve problems accurately, understand the physics thoroughly, share information transparently, and confront technical limitations directly. These principles guided the new generation of engineers, just as they had guided the original architects. The difference was scale. The company that once worked out of temporary buildings now operated across continents. Its systems were no longer experiments. They were foundational elements of global industry. By the mid-2020s, the geopolitical environment surrounding ASML had shifted from peripheral policy discussions to sustained strategic pressure. Governments had learned during the semiconductor shortages that advanced computing capacity wasn't evenly distributed and couldn't be increased on short notice. They had also learned that the highest value segments of the semiconductor supply chain depended on systems no country besides the Netherlands could provide. That realization placed ASML at the center of a global policy debate about technological self-sufficiency, national security, and economic resilience. The United States took the most assertive stance. It had already restricted the export of EUV to China, and had worked closely with the Dutch government to formalize those limitations. As competition between the US and China intensified, Washington pushed for additional restrictions, including controls on advanced DUV tools and certain subsystems that could support sub-10 nanometer manufacturing. The Dutch government, balancing its relationships with both the US and China, implemented new licensing requirements that further reduced ASML's ability to ship high-end equipment to China. These decisions had material consequences. China was a major semiconductor market, and its domestic foundries were among the world's largest consumers of DUV lithography tools. Restrictions on EUV hadn't slowed this demand. In fact, China increased purchases of DUV tools as part of its effort to improve manufacturing capabilities through multiple patterning techniques. ASML had to navigate these dynamics carefully. The company followed all export regulations but continued supporting customers within the rules. It maintained its position that export decisions were the responsibility of governments, not the company. Meanwhile, China accelerated efforts to develop domestic lithography capabilities. The most visible of these efforts centered on Shanghai Microelectronics Equipment, or SMEE, the country's leading lithography firm. SMEE's tools weren't competitive with ASML's advanced systems. They were aimed at far older process nodes, typically above 90 nanometers. But SMEE was working on a 28 nanometer immersion tool, and Chinese research institutions were pushing forward on components like stepper stages, control systems, and optics. These developments didn't threaten ASML's leadership in EUV, but they signaled a national commitment to closing the gap over time. The challenge for China was structural. Lithography wasn't a single technology, but a convergence of dozens of disciplines. Even if SME produced a 28 nanometer immersion tool, it would still need advanced optics manufacturing, light sources with sufficient power and stability, high-precision mechatronics, contamination-free vacuum systems, advanced metrology tools, and downstream process integration. Each of these areas required decades of cumulative expertise, and many depended on supplier ecosystems that had co-evolved with ASML and Zeiss. Replicating this ecosystem was possible in theory, but required time, stability, and consistent investment. Canon, on the other hand, experienced a resurgence in the early 2020s, not through EUV but through dry DUV systems. Their tools, while less advanced than immersion platforms, found strong demand due to shortages and increased production at mature node fabs. Canon had maintained strong capabilities in optics manufacturing and certain exposure principles, and industry constraints allowed the company to regain some relevance. Some analysts speculated whether Canon might re-enter the high-end market in the long term, but the company itself focused on areas where it could compete reliably. Nikon's position weakened further. Once the dominant force in lithography, Nikon had withdrawn from the race for EUV years earlier and shifted resources toward other imaging technologies. It still served parts of the semiconductor market, but no longer influenced the direction of leading-edge processes. The company's strategic decisions in the early 2000s, especially its hesitation around immersion and EUV, had left it with no credible path back to the top tier. As these changes unfolded, ASML's position became clearer. The technical barriers to entry weren't declining, they were increasing. Every new generation of EUV tools required more complex optics, more sensitive control systems, more advanced contamination mitigation, and greater manufacturing precision. The cumulative knowledge accumulated within ASML, Zeiss, and Cymer couldn't easily be reproduced by a new entrant. Even countries with strong industrial bases, such as South Korea and Japan, found it more practical to rely on ASML than attempt to build competing systems. This reliance introduced new risks. Concentrating global manufacturing capacity in a single company created a strategic vulnerability. Any disruption to ASML's operations, whether from supply chain instability, manufacturing delays, cyber attacks, or geopolitical conflict, could have global repercussions. Governments began asking whether it was feasible to diversify suppliers or establish redundant capacity. But diversification wasn't a simple matter of funding or political will. It required building expertise that could support long-cycle development, withstand failures, and maintain competitive performance as dimensions shrank. TSMC, which relied heavily on EUV for its most advanced nodes, recognized these risks but also understood the practical limitations of diversification. The company supported ASML through long-term commitments, joint engineering work, and infrastructure investments. Samsung and Intel maintained similar relationships, though each approached tool allocation differently. All three had an interest in ensuring ASML's production capacity could increase. They worked with ASML to communicate long-term demand forecasts, stabilize ordering patterns, and reduce volatility in development timelines. ASML, for its part, invested in expanding its manufacturing footprint. It built new facilities, added cleanroom space, and increased automation in certain assembly processes. The company also strengthened its supplier base by supporting expansions, training technicians, and standardizing certain design interfaces. These investments increased production capacity for both EUV and DUV, but they didn't eliminate the long lead times inherent in optics manufacturing and precision assembly. The company also engaged more deeply with policymakers. As export controls tightened, ASML provided technical briefings to government officials to clarify distinctions between tool generations, capabilities, and market impacts. These briefings didn't advocate for specific policies, but aimed to ensure that decisions were based on accurate technical understanding. ASML also collaborated with European institutions working on industrial strategy, recognizing that its success had implications for the broader European technology sector. Despite these pressures, ASML's focus remained on engineering progress. High-NA EUV advanced through prototype stages. New DUV platforms improved throughput and stability. Software optimization continued across the installed base. Service infrastructure expanded into additional regions. The company maintained its commitment to long-term development cycles, understanding that technological leadership required consistent investment over decades. As the global environment grew more complex, ASML's position remained defined by technical capability rather than strategic posturing. It didn't seek its role as a choke point. It acquired it because no other organization had taken on the challenge of integrating the extreme physics, manufacturing precision, and real-world process demands required to advance semiconductor scaling. Whether this position could be replicated remained uncertain. The barriers to entry were high, and the knowledge required was cumulative, interdisciplinary, and deeply embedded in institutions rather than individuals. China could make progress, but faced structural delays. Canon could sustain niche leadership, but couldn't challenge EUV. Nikon had ceded the field. No new entrants had emerged with a credible roadmap. As long as global semiconductor scaling depends on EUV and its successors, ASML will remain the central supplier. The challenge for the company isn't maintaining a monopoly, it's sustaining the technical, organizational, and geopolitical balance that makes continued progress possible. The next phase of EUV development and the demands of High-NA and beyond will test not only ASML's engineering capabilities, but its ability to operate within an increasingly fragmented global landscape. So where does that leave us? ASML started in wooden shacks with a handful of engineers who weren't sure the project would survive. Today, it is a company that governments treat as a strategic asset, that investors view as irreplaceable, and that manufactures machines so complex they take years to build and ship in dozens of containers. The machines themselves are almost impossible to describe without resorting to metaphor. An EUV system fires lasers at droplets of molten tin 50,000 times per second to generate plasma that emits light at 13.5 nanometers. That light bounces off mirrors so precisely engineered that their surfaces deviate by less than an atom's width. The wafer stage accelerates faster than a fighter jet while holding position to within a fraction of a nanometer. The entire system operates in a vacuum to prevent the light from being absorbed before it reaches the wafer. And all of this happens inside a machine that costs hundreds of millions of dollars and requires continuous monitoring, maintenance, and software updates from teams stationed around the world. It's the kind of technology that makes you wonder how humans managed to build it at all. The answer is that they didn't build it all at once. They built it over 40 years, through 6 consecutive years of losses, through spinouts and acquisitions, through partnerships that required two corporate cultures to learn how to work together, through feedback loops with customers who were willing to document their failures in detail? The answer is that they built it by solving one problem at a time, by refusing to stop when the physics seemed impossible, by maintaining a culture where technical accuracy mattered more than political comfort. There's something important in that story for anyone trying to understand how progress happens. It doesn't happen because someone has a vision and executes it perfectly. It happens because people keep working on hard problems even when the odds look bad, because institutions maintain their standards even when it would be easier to relax them, because relationships between organizations can sometimes transcend short-term interests. ASML didn't become indispensable because it was protected by government policy or because it got lucky with timing. It became indispensable because it solved problems that everyone else had given up on, and it kept solving them year after year, generation after generation, until there was no one left who could compete. That's not a comfortable story for anyone who thinks technology can be easily replicated or that industrial leadership can be purchased with subsidies. The knowledge embedded in ASML, Zeiss, and their suppliers took decades to accumulate. It exists in documentation, in institutional memory, in relationships between teams that have worked together long enough to anticipate each other's mistakes. Engineers who started in those wooden shacks are mostly retired now. The company they built employs tens of thousands of people across multiple continents. The machines they imagined are now foundational elements of global industry. And somewhere in Veldhoven, in labs that are considerably better insulated than the originals, the next generation is working on the problems that will define the next 40 years. They inherited both the tools and the demands of the most complex manufacturing technology in history. Whether they can sustain the momentum that brought ASML from obscurity to indispensability, that remains to be seen. But if history is any guide, they'll figure it out the same way their predecessors did, one problem at a time, with data instead of intuition, and with a willingness to confront technical limitations directly rather than hoping they'll resolve themselves. That's the ASML story, and it's still being written. There's a final observation worth making about ASML's trajectory, and it concerns the nature of institutional knowledge itself. When people talk about competitive advantages in technology, they often focus on patents, capital, or market position. These things matter. But the deeper advantage ASML accumulated was something harder to define: the ability to fail productively. Every failed prototype, every inconsistent tool, every customer complaint became data. And that data became understanding. And that understanding became capability that competitors couldn't simply replicate by reading a paper or hiring a few key engineers. Consider what it means to stabilize a plasma source that fires 50,000 tin droplets per second. The physics are well understood, the equations are public knowledge, but knowing the equations and knowing how to build a system that reliably hits those droplets, vaporizes them, collects the light, and directs it through an optical system while managing thermal loads and contamination, that's different. That knowledge lives in the accumulated experience of thousands of engineers who spent years watching things fail and understanding why. The same is true for the optical systems. Zeiss publishes research. The principles of multi-layer mirrors are documented in academic journals, but the ability to deposit 70 alternating layers of molybdenum and silicon with sub-nanometer precision to polish surfaces to smoothness measured in atoms, to do this repeatedly at industrial scale, that exists in the hands and habits of craftspeople who've spent careers refining these processes. Their expertise can't be transferred through a whiteboard presentation. This is why ASML's position is so durable. It's not protected by a single patent or a single innovation. It's protected by the integration of thousands of small innovations, each one learned through experience, each one essential to making the whole system work. Competing with ASML would require not just copying the endpoint, but retracing the entire journey, decades of learning, failing, and improving. Some observers find this concerning. A single point of failure in the global technology supply chain seems like a risk that should be mitigated, and they're not wrong to worry. But the lesson of ASML's history is that such positions aren't easily duplicated. They emerge from circumstances, from decisions made decades earlier, from cultures that form slowly and can't be manufactured on demand. The semiconductor industry has always concentrated expertise in unexpected places. Taiwan became the center of leading-edge manufacturing not because of natural resources, but because of institutional choices made by Morris Chang and his successors. The Netherlands became the center of lithography not because of government planning, but because of the specific conditions that allowed ASML to survive and grow. These concentrations create risk, but they also enable progress that might not happen in more distributed systems. Perhaps that's the most important lesson from this story. Progress in hard technology doesn't come from distributed effort. It comes from intense concentration of expertise over long periods. It requires organizations willing to absorb years of losses while learning. It requires partners willing to share information when conventional business logic would advise against it. It requires a culture that values technical accuracy above political convenience. ASML embodies all of these things. It's not a perfect company. It faces challenges, geopolitical pressure, supply chain constraints, the ever-increasing complexity of the physics it must master. But it has demonstrated something that many people doubted was possible. Europe can still produce world-leading technology companies. Industrial leadership can be built and maintained through engineering excellence rather than market manipulation or regulatory capture. The engineers in Veldhoven would probably say they got lucky. They'd point to the customers who gave them chances they hadn't earned, to the partners who stuck with them through difficult years, to the timing that allowed them to catch waves of industry transformation. And there's truth in that. Luck matters, but luck doesn't explain 40 years of consistent execution. Luck doesn't explain a culture that survived leadership transitions, market crashes, and technological disruptions. Luck doesn't explain the ability to attract and develop talent generation after generation. What explains those things is something simpler and harder to replicate. A commitment to understanding reality as it is, not as you wish it were. A willingness to be wrong and learn from it. A recognition that the physics doesn't care about your business plan. That's what started in those wooden shacks in 1984. That's what grew into the company that now controls the most advanced step in semiconductor manufacturing. And that's what will determine whether ASML can continue to lead as the challenges grow more complex and the stakes grow higher. The machines will keep getting more sophisticated, the physics will keep getting harder, the geopolitics will keep getting more complicated, but the fundamental challenge will remain the same. Understanding reality deeply enough to work within its constraints while pushing against its limits. That's the job. It always has been. And as long as ASML keeps doing it better than anyone else, it will remain indispensable. One more thing worth noting, the next generation of ASML's technology, Hyper-NA and beyond, will push even further into the realm of extreme engineering. The mirrors will need to be larger and more precise. The light sources will need to produce more power without increasing contamination. The wafer stages will need to move with even greater speed and accuracy. Every incremental improvement in resolution requires exponential improvements in precision. The question isn't whether ASML can maintain its lead. The question is whether the industry can afford to keep pushing forward. Each new generation of tools costs more to develop and more to manufacture. Each new fab costs more to build and equip. At some point, the economics of Moore's law may hit constraints that no amount of engineering can overcome. But that point hasn't arrived yet. And until it does, ASML will be at the center of the effort to extend it. The machines will keep shipping from Veldhoven. The engineers will keep solving problems that seemed impossible a decade ago. The partnership with Zeiss will keep producing optics that push the boundaries of precision manufacturing. And the relationship with TSMC will keep generating the feedback that drives improvement. 40 years from now, someone will tell the next chapter of this story. They'll describe technologies we can barely imagine today, challenges we haven't yet encountered, solutions that will seem obvious in retrospect, but impossible in prospect. And somewhere in that story, there will be engineers who inherited everything ASML built and used it as a foundation for something even more remarkable. That's how progress works. Not through sudden breakthroughs, but through accumulated understanding. Not through individual genius, but through institutional persistence. Not through luck, but through the systematic confrontation with reality that turns failure into knowledge. ASML figured that out in those wooden shacks. The next generation is still figuring it out in much better facilities. And in that continuity, in the passing of knowledge from one group of engineers to the next, In the culture that values accuracy over comfort, in the partnerships that make impossible things possible, lies the real story of how humanity builds the machines that build the modern world.